I currently work in the Cassandra Cloud Infrastructure team at Apple. If you saw Sankalp's talk earlier, we work in the same group, and we support many different applications, Cassandra installations within Apple. So you may have heard some rumors at the conference that we're pretty serious users of Cassandra. So yes, we are, and I can confirm that with this. We have quite a lot of data and quite a lot of nodes. We have, a total of more than 75,000 instances of Cassandra running in production today. They're serving tens of petabytes of data. And they do a few million operations per second. And some of our clusters are more than 1,000 nodes strong. And we're running various mixtures of 1.2 and 2.0 for the different applications. So yeah, we're pretty serious about this. So yeah, moving more on to the talk. So yeah, I want to talk about tools and give you some hints, and also explain a lot of internals to, because if you want to get deep down to solve problems in Cassandra, you do need to understand some internals, to dive into the code, and I also want to show you that's quite a lot of fun. And I'm going to illustrate this with some real-world examples, 3 examples of things that happened at Apple that I had a look at, and how I fixed them, how I diagnosed them, and maybe tell you how you could avoid them. So first one, uneven client latencies. So the setup for this is a cluster, has 2 data centers, and we do read and write at local quorum. So that's a very common consistency level for multi-DC deployment. If you do local quorum, it means that you can maintain consistency provided your reads and writes are on the same data center. It's likely consistent across the whole data center, but it's not guaranteed. But the great advantage is you don't pay the cross DC cost. So local quorum is a very, very common use case for a multi-DC setup. So that's what we use. But then we had a graph like this. So this is measuring client latencies, how long it takes the client to process a query. And most of them are very happy at like 5 to 10 millis. Great. But there was this one guy all the way up here at 80 millis. You know, what's going on with that client? So the first thing I looked at Cassandra. So you look in Cassandra, and everything looks pretty good. There's nothing wrong. In particular, storage proxy latencies were 4 millis. So before I carry on, I just want to carefully define what I mean by all these different latencies. So this is your Cassandra cluster, the ring, and your client lives somewhere outside and connects in. So your client connects to any node it wants to do its query, and that's called the coordinator, and then that fans out the request to wherever it needs to go. So the first thing is the client latency. That's what the client measures. That's pretty obvious. So then there's the storage proxy latency. So that's once the query gets to Cassandra, how long does it take? So that involves some parsing, some sending the messages out to the nodes doing their work, and then it coming back. So that's pretty much all of the time the query is inside Cassandra. So that's a very common thing to measure. And then the other one is the column family store latency. That's the latency once the request has got to the node that needs to do the work, how long does it take to do it? So how long does it take to do the insert, to do the read, to do some I/O if it needs to, or whatever it's doing. So that's like, that doesn't involve any networking in particular, that one. So some sort of rough relationships between them. The client latency is normally storage proxy plus the time it takes the client to reach the cluster. The storage proxy is the slowest node to respond that's required by the consistency level plus the internode network latency within your cluster. And then, yeah, the column family store latency is to do the work. So back to our problem, now we understand the latencies. The client latency is 70 millis greater than the storage proxy latency. So that's some networking delay, probably, between the client and Cassandra. So 70 millis is suspicious. It's close to the WAN latency. So maybe the client is connecting to the wrong DC. Maybe that's happening. So the first thing to do then is to go and look, where are the connections coming from? Are we getting connections from the wrong DC? So netstat. Netstat is great. Use it all the time in Cassandra because you want to know who's connecting to who. How many connections are there? Are there people connecting on the right ports? Are there enough connections? Are the connections balanced? It's a really useful tool. So looking at these connections on the 9042, the native protocol port, there's this one guy that stands out in DC1. Everyone else is connected from DC2. This one's connected from DC1. So yes, there is a client which is connecting to the wrong DC. So we found what we expected, but why is it connecting to the wrong DC, and what does that mean? So it means high latency. That was the symptom that we saw. But there's actually another impact which could be worse. Connecting to the wrong DC means we may be violating the consistency. So I said local quorum gives you consistency if your operations are within the same data center. But now they're not. Like suppose that your client's only ever connected to one DC, then you would get total consistency as though you were using quorum across your whole cluster, across a single DC cluster. But now we're connecting to the other DC, those consistency constraints may be violated. So this is potentially a worse thing than the high latency. So it's something that does need fixing. So how did we get into this state? Well, this is, I'm going to explain how your client chooses which DC to connect to. So using the DataStax driver, this is how you initialize it, something like this. The key components here are the DC-aware round-robin policy. That takes in a DC name. I've just made this function get local DC. And then it will only select nodes that are within that DC. And then there's also the contact point. You just give it one node or as many nodes as you want in your cluster. So then what it does is it goes and asks that node, tell me everything you know. There's this system peers table inside every node in Cassandra that stores what it knows about the other nodes. And you just query that and you get a list of nodes plus data centers. So then you can filter on that. So how can this go wrong? So let's think. The first thing that can go wrong is the client thinks it's in the wrong DC. So this is kind of a sort of conceptual thing. Your clients are almost identical, but they're not quite the same because the clients in one DC have a different config file to the ones in the other because they need to know that they're in the other DC. So this is kind of, you push it out, oh, there's one config file, let's push it out, and then you forget that actually you need two different config files for the different DCs. So that's kind of maybe a pitfall, but that didn't happen. So we didn't do that. But what actually happened was the driver was incorrectly connecting to the wrong DC. So I looked at the nodes that it was connecting to in the wrong DC, and I asked Cassandra, which data center is it in? And it returns null. So the driver is getting back a null DC. So what does it do there? Well, it turns out that it treats null as local. I don't know if that's good. Maybe that's the right thing to do. I'm not sure. If you don't know which DC it's in, maybe if it was one node, you could just ignore it. But suppose all of your nodes return null, then your client wouldn't connect to any and you'd have an outage. So maybe you'd prefer it to choose null as local and connect, or maybe you wouldn't. I'm not quite sure if that's the right thing to do. But the main problem is, why is there null? There shouldn't be a null in the first place. So I noticed that this node was new. It had recently been used to replace one that had failed. So I thought, well, maybe there's some bug in the replacement that means that the DC doesn't get set properly. So I created a test cluster on my box, and I did a replacement, and sure enough, the DC name was null. So we can see what the bug is. We have a reproduction. But I also found out that if you restarted the replacement node, then it would then propagate the DC. So we can work around this problem now. So it's not too bad now. We just bounce the node and it will come up. But we still need to fix it. So what you should do is file a JIRA. If you have a reproduction, filing a JIRA is amazing because there's always so many developers out there who will just take that and they'll fix it right away for you. So use the community. It's great. So I made a JIRA, and here it is, and Brandon fixed it for me. Thank you, Brandon. Okay, so we have a fix. That problem's solved. Let's move on to the second example. So this is sudden timeouts. The cluster suddenly started giving timeouts. So this was the latency graph. This is storage proxy latency from Cassandra. I've got the average, by which I mean mean, and the median and the 99th percentile latency. So the average goes up quite a lot. The median is the same, and the 99th percentile has shot up. So this is consistent with a few percent of your queries timing out. The timeout is 10 seconds. So that's the kind of thing you see when you get a few timeouts in Cassandra. Digging in a little bit more, only a few coordinators were giving timeouts, and they were giving a lot, but the others weren't. So there's some problem with a few of them. So maybe there's some disk failures, some errors causing them to time out, but no, the column family store latency is unchanged. The column family store is once the node gets the request to do the work. So that actually doing the work takes the same amount of time. And this is also for reads and writes. So they're quite different code paths in Cassandra. You wouldn't normally expect both of them to have problems. So this points to some networking messaging problem between some instances. That seems quite likely. So the first thing you should do when you get timeouts is have a look in the logs, because if there's an error, an exception that's thrown, then the node won't send a message back to the coordinator. You'll just get a timeout. So you should look for errors. So that's what I did. I looked at the coordinators that were giving timeouts, and sure enough, there's some errors. I'll go into this in some more detail later, but the important thing, well, first of all, the important thing when looking through Cassandra logs is with the default log4j config, they tell you which thread the message has come from. Every single message in the log tells you which thread. So here, it's the second one here, it's write-IP address. So we've got 3 exceptions here, actually, and they're writing to 3 different IPs. And it turns out that those IPs are replicas. So the write to the 3 replicas has failed in the write thread, so the write was never sent, so of course we got a timeout. And then actually, 2 seconds later, we got another error on the coordinator as well, which looks almost the same, but we can see further down the stack trace that it's in writing hints, and we can see that the thread is different. This is in the mutation stage. So the mutation stage in Cassandra is the thread pool that deals with writes. So if you get an error there, then that means you're going to get some timeouts. So this is it's a little bit suspicious. So the first thing, of course, you should do when you get exceptions you don't understand is search on Jira. So I did that. And there is a Jira, which is great, but no one has any idea what it is. So this is kind of why the slide I put up about the scale at Apple makes a difference, because stuff is big here. So if there's a bug, or even if the probability is low, we'll probably see it. So it's pretty exciting to see these things in the wild. So we have to go back to some analysis. No one knows how to solve this problem, so let's look at the code. So there's these 2 exceptions. The first one is a write timeout because of an assertion error. And the second one is the same assertion error, but this is in writing the hint. So that's kind of expected, because if you don't get a response from a write, then you write a local hint so that you can write the message later. But we're failing to even write the hint. So the write is just totally gone. So let's have a look at this assertion error in a bit more detail. So remember I said that it tells us which threads they're in. So if we've got a exception in a thread, then what has happened to that thread? What did it do with that exception? So very, very useful tool in Cassandra is to use JStack. JStack tells you what threads are doing, whether they're blocked, how many there are, which ones, whatever. Use JStack a lot. So I had a look for these threads, and they're gone. These write threads have died. So what could do that? So this is the sort of simplified version of the code in Cassandra that deals with the sending messages on connections. It's essentially you put stuff on a queue, and then there's a thread which takes stuff off the queue and writes it on the network. But we're getting an assertion error in the write. So we've got an uncalled exception. The thread is dead. So the thread has exited. So this is particularly bad because there's one queue and one thread per remote connection, and there's only one connection per node. So the connection is just dead. We're not sending anything to these nodes. In fact, we're putting stuff in the queue, and it's just building up. No one's taking anything off the queue. No one's writing it on the network. So every single message that this coordinator sends to these guys is just going to disappear. So this is why we're getting the timeouts, because basically these connections are just dead. We send stuff and they don't get there. So we need to understand why we're getting this assertion error. So the first thing to do is to restart it. We're getting timeouts. We need to restart. And then it's fine, because you recreated the connections. Everyone's happy. But then a few hours later, boom, it hits the assertion error again. So we really do have to figure out what it is. So let's dive into the code that actually does the assert that fails. Well, here's a simplified version of it. It's in the serialize method that serializes the row mutations. This is the class that encapsulates the writes that it's trying to send to the replicas. So it's writing it. It's writing the size as part of the serialized format. And then it's asserting that the size is greater than 0, which seems like a sensible thing to do. Why would you want to send a message that's empty? So that's failing. So somehow the message is empty. So is it possible to send nothing in a write? Well, a client can't do that. A client, there's no CQL statement which is insert nothing. You can't do it. So a client can't construct such a thing. So how can the insert statement that was given be modified to remove everything from it? So I didn't really have any ideas at this stage. So I looked at every call to create a row mutation object. And I think there are about 20 of them. So just look through each one in the code and see, is it suspicious? What could go wrong? So I found one that concerned me a little bit from counters. So a little bit of background on counters. So counters in Cassandra are sharded counters. So each replica has its own count. So if you've got replication factor 3, you've actually got 3 counters. And the value of the counter is the sum of these 3. So when you do an increment to your counter, actually what you do is you choose one of the replicas, and you send it to the increment, and it writes the increment. That's just a normal column. Well, it's a counter column, but it's essentially like a normal write with a flag saying this is a counter. But then the replication is totally different. So this is one of 2 cases in Cassandra where writes actually entail a read. So you write this increment, and then you read back the full value. So say you had the counter was 99, and you do a +1. So you write +1, and then you read back the value. So you get back 100. And then you send that message out to the remaining replicas to say, oh, this is the new value of my counter. So it's quite a lot more complicated than a normal write, this is. So there is a read here. So this is why it might be suspicious. So here's the code that deals with the counter replication. So this line here does the read, and then we return it. But there's nothing to check that we actually read anything here. We constructed this row mutation. This for loop is just because maybe we're doing a batch across multiple column families or key spaces. But no one actually checks that we got something back from that row. Maybe it was empty. So how could that be empty? Well, I got a bit suspicious at this stage. So I remembered that for counters, the timestamps, so here the timestamps are for each shard value, there's a timestamp. And I remembered that those were automatically computed. You can't specify them from a statement, a CQL statement. They're just specified to be milliseconds into the epoch, which is non-standard. So almost everywhere in Cassandra, the timestamps are micros since the epoch, including counter deletes. So now I got very suspicious. So deletes are basically an insert, again, with a timestamp. So we're inserting something with a timestamp in micros over something with a timestamp in millis. So this is what is known as a Doomstone. So a Doomstone is a delete with a timestamp in the future. So what that means is if you try and insert, it's as though you hadn't done it because someone has deleted it in the future. So you do an insert, and it's just going. It's disappearing. So a counter, actually it's the row deletes rather than counter deletes that use micros. A counter row delete is effectively a Doomstone because the timestamp's 1,000 times greater than what it should be. So increments after that are just lost. So actually what happens is when we do that read, we get back nothing because there's a Doomstone there. So this explains what's going on. We write our increment, we read it back. Oh, it's been annihilated by the Doomstone, so the read inside Cassandra is doing what it should do. It's returning nothing because it's been deleted. So we then send this empty row mutation around. The assertion fails. We can't serialize it. We can't send it. We kill the writer connections. We get timeouts for all other operations on these nodes. So this is the root cause of the problem. So again, we have a reproduction, and there is even a JIRA already. So let's write it on the JIRA, how to reproduce it. And the fix is, yeah, just don't send the empty counter mutation. So actually, the reason why I've put these screenshots from the JIRA here is to look at the timestamps. So I found the reproduction at about 3 p.m., and by 4 p.m., there was a fix. So thanks, Alexi, for doing that pretty quickly. And it's also great. I've never met Alexi. Maybe you're here. I don't know. It'd be good to meet you if you're here. So someone will fix the bugs for you within an hour. Although, actually, it turns out that fix didn't work. But 2 hours later, it... 2 hours later, it did work. So in the afternoon of finding reproduction, we had a fix, which we verified, and it worked. So that's pretty awesome. And a sort of summary of all this stuff is counter deletes are bad. So sort of subtle points, but with counters, increments commute with each other. The order really doesn't matter. But if you delete in a different place, then it does. And in Cassandra, compaction may happen in different ways. So if you've got deletes if you've got some deletes there and some increments there, some made before the delete, some made after the delete, then actually the value you get out depends on the order of compaction, which isn't great. So you shouldn't do deletes with counters. So actually, that JIRA that Alexi fixed was to not send the empty mutation, but there was a side JIRA which was we should use the same timestamps. But actually, we decided that the best thing to do was use the timestamp long max value for the delete, because you don't want to reuse it. You do actually want the Doomstone there, because it means that you just can't reuse it. If whenever you do your testing, you'll realize that it's gone and it's not there. So actually, the fix is, don't kill the connection if you do this, but actually, don't do deletes and reuse your counters. I mean, this is the recommendation, but it's pretty subtle. Okay, there's some counter stuff. So on to the last example. So this is deleted data reappearing. There's a little bit of overlap with some things that Sankar worked on if you went to his talk. But I'll explain a few other use cases as well. So here's what happened. We wrote some data, and then we deleted it, and then we didn't read it. And then we waited months. Everything was happy. And then suddenly, this data was there again. Where did it come from? Why is it there? What happened? So a little bit more on Tombstones. So as I said earlier, Tombstones, they're inserts. They're just like normal inserts with a flag saying delete, and they have a timestamp for ordering. But you don't want these to hang around forever, because then you can never reclaim the space. So there's this thing called GC grace, which means that the Tombstones will live for at least that long. So there's complications about when you can even get rid of them after that, because you have to know that you've compacted it with all other versions of that column to make sure you're not just going to get rid of this Tombstone when you've still got some live value somewhere else. So the code that does that is a little bit subtle. So the obvious thing that can go wrong, this is what Sankar was talking about with repair, is if a replica misses the Tombstone, then the other guys expire theirs, and then you do a read or you run repair, and the data will come back. So this is why you must run repairs every GC grace. So, of course, everyone does that, so that's fine. So that didn't happen, but this did happen. So a node had restarted. So I had a look in the log when it was starting up, and what it does is it loads each SS table. But then there was this exception on one, EOF exception. The file's corrupted somehow. Okay, corruption happens, fine. Actually, just before I move on to explain that, the way of figuring out which file is corrupted is a little bit of a pain. That's why I've highlighted those 4s, because the only way to find out is to match the thread names. So you can see the thread with 4 is printing out opening that file, and then later on we get the exception because it's doing it in parallel. So the way to figure out actually which file is corrupted is you have to match the thread names there. So that's how you do that. So how could this actually cause our problem? Well, one SS table has got corrupted, and we've skipped it as though it was deleted. So this could, suppose this SS table had our tombstone in, but the other SS table didn't. Another SS table had a live value. Well, now we've lost the tombstone. So I verified actually that this instance that had restarted owned the key that had come back to life. So yeah, if you actually, I've got a little diagram here of how it works. You've got these 2 SS tables. By X, I mean delete. And then if someone kills that one, then you now have the value back. So a corrupted SS table can lead to data gain rather than data loss. It could also lead to data loss, of course, but here it actually led to data gain, which is bad too. So actually, why did we even get this corrupted SS table on start? Well, it turns out that this server had suddenly rebooted. Maybe there was a power problem, memory problem, I don't really know, but it suddenly restarted, and the last written SS table had been corrupted. It wasn't fully written to disk. So that's what happened. So what you should do is not use the data on that node, because maybe we've lost a tombstone. So I actually created this JIRA to fail startup if any problem is found, because we don't want to touch this thing because maybe we've brought some data back. Okay, so this is very rare. We don't get these servers randomly rebooting at that time. So this hasn't happened, and we're careful, so it's good. But then a few months later, we had the problem again. So here it was totally different, and I had a look, and you sort of get a feel for how things should look in your healthy cluster. So when you just have a poke around and you just feel something's a little bit wrong. So notice that some SS tables were quite old, which is a bit surprising because you'd expect them to get compacted with newer ones. So the timestamps are all fairly new. So these ones weren't compacted. So I thought, there's something a bit suspicious there. So I took a snapshot, and the files weren't in there. So what I mean by this is this is your data directory. There's the old ones from July and the new ones from August. Take a snapshot, and it's only got the ones from August in. So if a snapshot doesn't contain SS tables, it means those SS tables are blinds to Cassandra. It's as though they're not there. So those files are just hanging around in the data directory, and we're not using them. So why are they there, and why is this bad? Well, turns out that date in July coincides with a failed repair. So repair fails for many reasons, hardware failure, nodes go down in the middle, disk failure, disk fills up, whatever, it happens. So I had a look, and there's this JIRA. The problem is that when you run repair, you stream the data in, but if it fails in the middle, it wasn't deleting the old data. So if you stream in from a node an SS table that has a key, and you would later on stream in a tombstone that kills that key, but you don't because it died before you got there, then you've streamed in the value but no tombstone. So now it's kind of like the case before where you've got a corrupted SS table and you skip it and you lose the tombstone. So when you restart this box, it doesn't know that these files are old. It just says, oh, there's files in the data directory, let's load them. So this is why it takes months, because they don't restart very often. So this failed repair happens, and then sometime later you restart, and you get data coming back. So when you realize this is happening, well, you have to go and clean up these blind files that you can't use before you restart. So you have to write these scripts and be careful with restarting your instances. So yeah, so we did that. We had to remove these orphan files before we restarted. A little bit more generally, actually, streaming in general, you do have to be careful. Streaming happens when you do bootstraps, decommissions, moves, that's when you shift a token, and on repair. And actually, if any of these things fail partway through, you have to delete everything that you got. Otherwise, you're going to get exactly the same problem. So with that fix, that always happens except for on Bootstrap. So suppose you're bootstrapping a new instance and it fails streaming in the middle. Again, maybe there's a network problem, the node it's streaming from dies, whatever. You're probably going to try again because you still want to bring this guy up. So you restart it and you bootstrap, and then you could have the same problem. Maybe you've streamed an SS table with data and you've missed the tombstone, and now the tombstone's been garbage collected away, so you don't stream it up and you get data coming back to life. So what you should do is if you get a failed stream on Bootstrap, you should wipe it clean before you start again. Otherwise, you could have this problem. OK, so we did that. We've got that fix. And then again, we got some more data coming back to life. So this is quite similar. So again, there were some old SS tables. So I thought, oh, no, that bug has come back. But no. Even though it was still related to repair, actually this time it was on the stream out side. Before it was on the stream in, but this is on the stream out. And the reason why you can tell that is because when Cassandra is streaming out files, it actually prints in the log, it is streaming out these files to where. So you can see that these files were listed there. So it was streaming them out. But if the repair fails, these files were then hanging around. So maybe there was a problem with SS table reference counting. So actually inside Cassandra SS tables, there's reference counts to know whether a file is being used or not. So every time you do a read, it increments it. Every time you do a compaction, and you can then decrement it to delete the old one. And then when it goes down to 0, it deletes the file. So if there was a bug so that the reference count never went down to 0, then the file wouldn't be deleted. Even though it's not being used anymore, it's still there. So it's kind of similar to before, except it's in the stream out case. So I had a good look through the reference counting and noticed there was one case where the reference counting didn't quite work. This case was if the stream out failed immediately. So this would happen if the node you're streaming to dies. So it sends the message, please give me this stuff, and then it dies. Then the guy who wants to stream out will say, oh, good, I'm going to get all these references to these SS tables, and I'm going to start streaming them. Oh, it's failed. Let's exit. And then it didn't call the release reference code. So these guys still had references on, so these references were basically leaked. So that's kind of bad for many reasons, like these files are just hanging around, wasting space. But then, yes, these files, when you next bounce, you'll pick them up and you can bring data back. So that's painful. So now that's fixed. The data coming back to life problems are solved, finally, fortunately. OK, so those are my examples. So I wanted to kind of, well, there's not really a summary from those examples, but just wanted to give you a few sort of more general tips from what we found. So first thing is Cassandra, it's running in a JVM. You should use all the standard tools you use for any Java thing. You can use JStack, JMap, whatever you use for any Java application. And also OS tools, netstat for networking, super useful, LSOF, all the tools that you use for any Unix app, you should use on Cassandra, and they'll tell you a lot of useful stuff. Another thing that I find is very useful is to try and isolate the problem. So often your client sees 2% of things time out, and it looks like the whole cluster is broken because everyone's timing out. But then when you drill down, you can see actually the timeouts, well, maybe the storage proxy latencies are all quite similar because storage proxy routes to other nodes. It's essentially random which ones they go to from the coordinator. So the storage proxy latencies may all look bad, but the column family store latencies may be different. So if one guy is being slow, maybe it has a disk failure or it's doing lots of GC, then that replica will be slow for everything, and that will slow down all the storage proxy latencies. But everyone else is fine. The root cause is this one node. So you drill down as far as you can, and then you may see one thing stick out that's totally different, and then that's the one you need to fix. And then maybe if you just kill that one, then everything is solved, or you have a look at it and you try and figure it out. So I guess what looks like a sort of global cluster problem is often isolated to just a small thing, and if you drill down with your monitoring, then you can do that. So having this sort of instance level monitoring is very important. You may have noticed that I had quite a lot of snippets from code here, so having the code available is very useful. So even though understanding how all the code works, there's a lot of it, it's quite a daunting task, but you get in all the logs the line number and the file that it came from. for a stack trace, you know exactly where it is. So if you see this, you can go and look up in the code. Even if you don't know the code that well, go and have a look. You'll see where the exception's getting thrown, the assertion, whatever. And maybe you'll have some idea of what's causing it. And then I guess you can just keep on looking a bit and you'll learn more about the code. But if you just look, maybe there's a comment there that tells you something useful. Maybe you'll just see a bit more about what's going on with that exception and you can figure out what's going wrong. So having the source available is very good. It's an open source project, so make use of that. So the last thing, use the community. The community is awesome. If you have a reproduction of a bug or feature suggestion, create a JIRA and someone will look at it and someone will fix it. There's always people who want to do that, so go and do that. Okay, last slide. This may look familiar if you went to Sankhalp's talk. We are hiring. If problems like this sound interesting, then please come and talk to us and you can work on them. So thanks very much.